Okay, we've already discussed how to find the exact area under a curve. And this is section 5.5. Strangely, we're going back to approximating the area under a curve after learning how to find the exact area. We learned that finding the exact area involves finding the antiderivative, plugging in the two limits of integration, and doing a difference. So that's how we normally do it. This actually gives us the area between the curve and the x-axis, remember? And it gives us the signed area. So it is possible to actually get negative area, in that case, the definite integral. Okay, but we would like to talk about one more approximation method called the trapezoidal approximation method because it shows up on the AP test quite often. Okay, so first let's review how to do LRAM, RRAM, and MRAM. So we're going to actually be going on the interval 1 to 7 here. So if we were to do LRAM rectangles, our first rectangle would look like this, with the leftmost point bumping up against the curve, like that. Okay, so the first rectangle you can see has a width of 1, and it has a height of whatever f of 1 is. Okay, let's go on to the next one. Okay, the next one would be this red one. We're doing LRAM, like that. And we can see that the width is still 1, and the height is now f of 2. So the area of that rectangle is base times height 1 times f of 2. The third rectangle, we'll just switch back to blue, would be this one. Again, it has base 1 and height f of 3 this time, f of 3. And this just alternates back and forth between the two colors here, and the next one would be f of 4, and the next blue one would be at f of 5, like this. And the last one would be a red rectangle at f of 6. So basically, instead of constructing one at a time, we could just basically assume that this goes on until we reach 1 times f of 6. Okay, now there's a function given right here, right? So we could just go ahead and use the calculator to come up with things like f of 1, f of 2, and so forth. Okay, so let's go ahead and do that real quick. Let's get the calculator up and running. Alright, and we're going to go ahead and turn it on. Go under y equals, so let's enter that function there in yellow. So it's x to the third minus 11x squared plus 34x minus 12. And I find the easiest way to get answers is to put the calculator in ask table mode. So I'm going to find f of 1, f of 2, f of 3, f of 4, f of 5. Oops, that's 45. 4, 5, and 6. Alright, so these are my values: 12, 20, 18, 12, 8, 12. That's nice. Alright, so let's go ahead and do one more thing. Before we add up the y values, we're going to go ahead and factor out that 1. You might say, that's silly, Mr. Shore, but understand that the base is not always 1. On these triangles it was, on these rectangles it was, but I'm trying to make this to where I'm just adding up the f value. So I pulled the height of, or the base out of the calculation. Okay, so these values were, let's look at those again real quick, 12, 20, 18, 12, 8, 12. So it's 12, 20, 18, 12, 8, 12. So 12, 20, 18, 12, 8, 12. That's correct. Okay, so there you have it. And this all adds up, of course, and gives you your final answer. And the answer is simply 82 square units. Okay, we can do the same thing using the RRAM method. The difference is kind of where we start everything, right? So let's go ahead and take a look at that construction real quick. So the idea on this one is you start on the right side of the first interval. Remember, we're still going from 1 to 7, so our first rectangle is still here, but we want the right endpoint of it to bump up against the curve, not the left endpoint. So this first one has area 1 times f of 2, not 1 times f of 1. Okay, the next one, the next rectangle will be designed like this, actually. Sorry about the red dot there. Okay, so it's going to look like this, where the right endpoint, that is at 3, is bumping up against the curve. It's on the curve. Okay, so that second rectangle basically has area 1 times f of 3. And this just goes on until we reach the last rectangle, only this time the last rectangle is at f of 7. In other words, its height is f of 7, see? So your last rectangle, let's see, it's going to go blue, red, blue, red, blue, red. It's going to be a red rectangle. It's going to be located right here, see? And it's going to have for its height f of 7. All right, so the last one is going to look like 1 times f of 7. In other words, if we factor out the 1, it looks like this for our RAM. It's f of 2 plus f of 3 plus etc. all the way up to f of 7. All right. And there you have it. And the answer to that one comes out to 100. 100. Okay, and then we have the method where you use the midpoint to construct the height of the rectangle. So we can actually still keep these widths like this, but the tops of the rectangles look different. So we'll start like that. How do we construct the heights? Remember, what you do is you go to the middle of the interval, which is right here, and you construct your rectangle to that height. So you go to the middle of the interval and you construct your rectangle to be that height, and so forth. And you just keep doing this from the middle. And we saw that this actually is a significantly better approximation to the actual area of the curve. Now, if we're using 1,000 rectangles, they're all good. You know, they're all really good approximations. But this right here is only 6 rectangles. MRAM is actually fairly accurate. Okay, so this would look more like this. The width is still 1, but the height is f of 1.5, and then it goes plus, and then it's going to be, for the second rectangle, base 1, f of 2.5, the last rectangle being when you reach f of 6.5. So the last one is f of 6.5. That's going to be a red rectangle, so 1 times f of 6.5. Or if you factor out the 1, we have f of 1.5 plus f of 2.5 plus f of 3.5 and so on, all the way up to f of 6.5. But the calculator also can do this, as you know, and you get actually 89.5 for this. Notice that the MRAM is not actually the average or anything of LRAM and RRAM. So it'd be really tempting to think, next time I'm just going to kind of average the 82 and the 100. Well, the average of 82 and 100 is unfortunately 91, not 89.5. So you cannot use that logic. Now there's an entirely different way to find the area, and that is using trapezoids, not rectangles. So let's take a look at how that might appear. So we're going to try to do this with 6 trapezoids now, from 1 to 7. Okay, so the trapezoids are going to look like this. Again, that's the first trapezoid. Only the top right endpoint and the bottom left endpoint here are both being used. So notice we're not actually drawing a rectangle. This is a trapezoid. It connects AF of A to BF of B. So it's a secant segment there. The next one would look like this, connecting these 2 points for the top, and something like that. The third one would connect this point to this point. That third one, notice the top of that trapezoid follows the curve pretty well, doesn't it, it seems? It's a pretty good linear approximation, you could say. The next one would be the red one, looks like this. That one is a little bit over approximating. Redraw that one. So let's do this and this straight line. There you go. And the next one is this one. I want a decent picture for this. And my last one looks like this. Very different look with the trapezoids in there. Notice that all the trapezoids connect one to another, so they kind of run together a little better and they're not so jagged looking. So there's another reason why it just gives us a better approximation. Okay, that's the drawing. And let's just look at the drawings of each trapezoid independently on the side here. So this first one has actually a height of the trapezoid. A trapezoid's height is determined by looking at the distance between the two parallel bases. So since these are parallel, we call this the height, this segment down at the bottom. It is the distance between the two parallel bases. Okay, notice that the sides or the legs, or sorry, the bases, of the trapezoid are actually f of 1 and f of 2 respectively. See? All right. Now the second one looks more like this. Right? And its sides are f of 2 and f of 3, and its height is 1. And the third one looks like this. Height is 1 again, but the sides are f of 3 and f of 4. See? And the last trapezoid, so we'll just do a dot, dot, dot here. The last trapezoid is a red one. It looks like this. And the height is 1. And the height is 1. The two bases are f of 6 and f of 7. Like that. Okay, now let's talk about the area of a trapezoid. So you probably remember from your SAT classes or whatever, you studied that the area of a trapezoid is 1/2 times base 1 plus base 2 times height. So for this first blue trapezoid, for example, the area would be 1/2 times f1 plus, f of 1 plus f of 2 times the height, which is just 1. Okay, and then the second one would be area equals 1/2 times f of 2 plus f of 3 all times 1. And this just goes on and on. Okay, so now that we kind of have the basic idea, we can see that the area of an individual trapezoid is going to be the area equals 1/2 times, and there's going to be 2 y values added, and then there's going to be the base, or it's actually the height of that trapezoid. So just 1 in this case, h in general. Sorry for the noise in the hallway. I told them I was busy, but okay. Anyway, I wasn't angry. Let's move on. So you can see that basically the area of a trapezoid is always 1/2, and there's 2 y values here added, and then there's the h. So that's kind of the way it works. All right, let's go ahead and go down and find the area of our trapezoid set. All right, let's see here. So everything kind of starts at f of 1, and then it ends up ending at f of 7. Okay, so the area of the first trapezoid is going to be 1/2 times f at 1 plus f at 2 times the height. The area of the second trapezoid is 1/2 times f at 2 plus f at 3 times the height, and so on. And this just goes on and on, one trapezoid after another. All right, I'm not sure what happened there. Oh, that got erased. That's okay. Let's keep working. So the total area, okay, the area using trapezoidal method, if you wanted all of it, you'd have to add up all those trapezoids together. So notice that each trapezoid has a 1/2 in it, so you could pull that out if you want. And then there's basically a sum of 2 y coordinates. So the first y coordinate, we could just call that like y0. I mean, why not? Let's just call it y0. Okay, so it'd be y0 plus y1. So that's like the starting value of the y coordinate, and then the next one, times the height. The height is just basically, you could say x1 minus x0. It's actually kind of looks like a width. Okay, plus, next one's going to be y1 plus y2, and then it's going to be x2 minus x1. And this will just continue on until you reach the last rectangle. Okay, now for most of our problems, we have the delta x is all being the same, right? So this is your height of your trapezoid. You could just pull that out. So we could abbreviate even further by doing this. Just do h over 2 like this. And then if you look on the inside, now that you've pulled out all the h's, these are all gone now. And the h is out front, see? Out here. So you basically end up with y0 plus y1 plus y1 plus y2 plus y2 plus y3 plus y3 plus y4. In other words, you're going to get y0 plus a pair of y1s plus a pair of y2s plus etc. all the way until you get towards the end. Then there's going to be a 2 times something, so we'll call it y sub n minus 1, and then there will be a y sub n. So the first and the last terms do not have a 2. But the middle ones all do have a 2. Okay, so you don't have to erase, but I kind of need to. And I'm going to get that answer right now. Okay, so here's the answer for our problem. The area using trap method, which we'll just call T. You know, we've used MRAM, RRAM, LRAM, and now we're going to use capital T. T is going to be h over 2, so h is just 1 for each trapezoid, times, and then it's going to be f of 1 plus a pair of f of 2's plus a pair of f of 3's plus a pair of f of 4's, I need a 2 there, plus a pair of f of 5's plus a pair of f of 6's plus a lonely f of 7. So the first and last do not get doubled up. Okay, and then according to my calculator, I had already looked these up earlier, if you recall. So remember, I had everything right in here. Hopefully it didn't all get erased. If it did, then we'll just redo it. Here they all are, and I need f of 7 now, so I'm going to include that. Okay, so the values are basically 12, 20, 18, 12, 8, 12, etc. So I'll just write these in. 12, 18, 20, 12, 8, 12. I wrote that wrong. It's 12, 20, 18, 12, 8, 12. Let's fix that. 12, 18, 20. 12, 18, I did it again. Mr. Shore. Okay, 12, 20, 18, there we go. 12, 8, 12, and then the last value, this is new, is 30, 30, 30. Okay, so, sorry about the slop. Notice that each of these is getting doubled, except the first and last ones. Alright, so the answer turns out to be 90. Interesting. 90. Where have we seen 90? I'm sorry, it comes out to 91. Where have we seen 91 earlier in this lesson? Well, if you go back in part A, we had done LRAM and RRAM. And remember, they had come out to be 82 was your LRAM, remember? And 100 was the RRAM. 100 was your RRAM. Notice that the average of LRAM and RRAM gives us the trapezoidal approximation. Interesting. So in other words, if you average these, you get 100 plus 82 all over 2, which is 91. What seems to be the relationship between LRAM, RRAM, and T? It would seem that T is the average of LRAM and RRAM. Interesting. Very interesting. Okay, so that's their conclusion. All right, now let's go back and just use do the definite integral. So our function, remember, is still up here at the top of the page. All right, let me scroll back down. Okay, so what you can do is just actually run through and do an antiderivative, get the exact area if you want. So the antiderivative of that integrand is 1/3 fourth x to the fourth, right, minus 11/3 x cubed plus 34/2 x squared, and then minus 12x plus a constant, and we're evaluating between 1 and 7. So this is the antiderivative of what we started with. Basically, I just added a power to everything, and then every time I added a power, obviously I got a new number. I just put that on the bottom. So, for example, when I added 1 to my x cubed, I got x to the fourth, and then I put a 1/4 out front. So this is kind of how you do polynomials. Antiderivative is pretty straightforward. If you take the derivative of this, trust me, it comes out to be what we started with on the interior. Now if you plug in 7 and 1, right, and then you subtract, you're going to end up getting the definite integral for this. So that's going to give you the exact area under the curve. Okay? Okay, and then if you plug in the 7, what you actually get is 1099 over 12. I worked it out just a moment ago. And if you plug in the 1, you end up getting, give me 1 second here. Okay, you end up getting 19 over 12, which of course gives you 1080 over 12, right? Which is actually the exact answer, and there's no approximation to it at all, right? The answer is exactly 90, in fact. 90 on the money. 90. Okay? So we got various answers today. We got 100, we got 82, we got 91. The exact answer is 90. You can see that actually the trapezoidal method was very, very accurate, as was the MRAM. The MRAM was 89.5, I think it was. Yeah, and that was pretty close to 90. And the trapezoidal method was 91, which is also pretty close. Okay, we're not trying to compare all the methods today, but we are trying to talk about how these are related, and so we can see that T, trapezoidal approximation, is the average of LRAM and RRAM. That's a great takeaway from today. And so I tried to put some formulas down at the bottom here for you. You really don't need formulas. You need to understand how to construct the trapezoids, and you need to know how to basically add up their areas. Okay, but if you need a formula, this one right here is good when all your h's are the same, so every single subinterval is 1, like I was having, or maybe they're h a half. That's your h out front, and that factors out. If all the h's are different, then you'll just have to have different heights distributed in. In other words, you might have to use this formula down here, where your various heights are all different. Okay, so this would be like height 1, height 2, and so forth. And so they're all different heights. And then each of these is like a base 1 plus base 2 over 2. Base 1 plus base 2 over 2. Base 1 plus base 2 over 2. Giving you sort of the areas of each trapezoid as you go. Alright, there's no reason for this blank here, but just know that this is a more versatile equation. It's a little hard to remember. The best way to learn this is to just know how to find the area of one trapezoid, to draw the trapezoids in, and then just find the total area that way. There you go. That's 5.5.